For billions of years, the universe kept a secret, whispering it into the void, hiding it in the faintest shadows of existence. But in the middle of the 20th century, with telescopes pointed at the invisible and instruments tuned to measure the cosmic silence, humanity stumbled upon an echo, a soft, persistent hum that filled the universe in every direction we looked. This discovery would transform our understanding of how everything began. It would provide the strongest evidence yet for the Big Bang theory and cast new light on mysteries that have puzzled philosophers and scientists for millennia. This echo is the cosmic microwave background, the footprint of the Big Bang. To unravel why the cosmic microwave background, or CMB, is so profound, we first need to journey back nearly 14 billion years. Imagine the universe not as the vast expanse of galaxies, stars, and planets we see today, but as something far smaller, far denser, and unbearably hot. A primordial soup of energy and elementary particles crammed into a volume billions of times denser than a star. In this unimaginable furnace, there were no atoms, no molecules, not even nuclei. The searing intensity kept everything apart. This was the earliest moment we can currently fathom, the birth of time and space itself, the Big Bang. In that dazzling instant, the universe wasn't just born, it began to expand, rapidly, and as it expanded, it cooled. Just fractions of a second after the Big Bang, the newborn cosmos was dominated by energy, with matter as wisps, quarks and electrons scattered in a fog of photons, unable to bond, unable to create anything more complex. Light, in this early era, was unable to travel freely. It was perpetually scattered by charged particles, like sunlight caught forever in a thick, swirling cloud. But the universe did not remain an opaque blaze for long. About 380,000 years after that first moment, a mere blink in cosmic terms, the relentless expansion cooled the universe to just under 3,000 degrees Celsius, finally allowing protons and electrons to come together and form hydrogen atoms. This seemingly simple event was revolutionary. With the birth of neutral atoms, the universe became transparent. Suddenly, those once trapped photons could travel vast distances unimpeded. The first light, free at last, began its interstellar journey. That light, stretching outward across the unfurling fabric of space, is the cosmic microwave background. It is the afterglow of creation, a snapshot of the moment when the universe first became visible, carrying with it information about the state of everything that existed mere hundreds of thousands of years after time began. Yet, if these photons were set free with energy fiery enough to rival the surface of a star, why do we today perceive them as a faint, cold drizzle of microwaves? The answer lies in the continuing expansion of the universe. As space stretched, so too did the wavelengths of the ancient light, becoming longer and longer over billions of years. What was once searingly hot, radiation cooled, its energy dwindling until, by the time it reached Earth in the 20th century, it took the form of microwaves, with a temperature just a little less than 3 degrees above absolute zero. For centuries, the human race had no idea this ancient light existed. Theories about the origin and fate of the cosmos abounded, but all were hampered by a profound lack of evidence. That would begin to change in the early 1960s, when two radio engineers, Arno Penzias and Robert Wilson, working at Bell Labs on a large horn antenna, tried to tune out an annoying static, a persistent background noise that refused to go away. No matter where they pointed their instrument, or how carefully they cleaned it, even scraping away what they thought to be pigeon droppings, they found the static remained. The signal was uniform, coming from every direction, at precisely the right temperature predicted by theorists for the leftover radiation from the Big Bang. Unbeknownst to them, a group of physicists at Princeton University, led by Robert Dicke, had been searching for precisely this radiation, a relic signature from the birth of the universe, theorized some 2 decades earlier as a direct prediction of the Big Bang. When the two groups connected, the realization was world-shaking. The CMB had at last been found. With this discovery, the universe's early history came into clearer focus. Before, many had treated the Big Bang as just one of several competing cosmological theories. The discovery of the CMB was a game changer. Suddenly, there was physical evidence everywhere, and it painted a universe that began hot, dense, and small before cooling and expanding into what we see today. But the CMB isn't just any fossil. It's one that tells an intricate story. Let's consider what it represents. Every time astronomers tune their telescopes to microwave frequencies, they are, in essence, looking back in time, gazing at the universe as it was less than 500,000 years after its birth. These photons, traveling billions of years across space, have witnessed everything, from the birth of the first galaxies to the formation of planets like Earth, and ultimately, the rise of human life capable of looking back at the universe's origins. Yet, what makes the CMB so revolutionary isn't only its existence, but its subtle texture. Early measurements showed the microwave background to be astonishingly uniform, with only minute fluctuations in temperature, differences tiny, just tens of millionths of a degree, but profound in their implications. These variations are cosmic fingerprints, the seeds from which all structure arose. Where there were slight overdensities of matter due to quantum fluctuations in the infant universe, gravity took hold, drawing matter together across eons to form stars, galaxies, and ultimately the grand cosmic web. Decades of increasingly sensitive satellite missions, the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have measured these variations with exquisite precision, mapping the infant universe in breathtaking detail. The patterns seen in the CMB reflect the universe's first physical processes, waves of pressure, acoustic oscillations, set up in that primordial plasma, freezing in place when atoms first formed. These patterns didn't just confirm the Big Bang, they became the cornerstone of modern cosmology, allowing researchers to measure the universe's age, composition, shape, and even its fate. From the CMB, we've determined the age of our universe, approximately 13.8 billion years. We've measured the density of matter, both the ordinary atoms that make up stars, planets, and ourselves, and the mysterious, invisible dark matter that outweighs all the rest. And intriguingly, we've discovered that most of the universe's content is neither matter nor the light itself, but a strange entity known as dark energy, responsible for accelerating cosmic expansion. Beyond the numbers and data, the CMB represents a triumph of human curiosity and ingenuity. It is a snapshot older than any fossil, older than our planet, older than galaxies themselves, a light left over from a time when the cosmos was in its infancy. Each photon from the CMB has traveled unthinkable distances, untouched and undisturbed, carrying a silent message across epochs. The universe began hot and dense and has been expanding, cooling, and changing ever since. Yet the CMB also invites new questions. The nearly uniform temperature seen in every direction raises a mystery. How could widely separated regions, too far apart in theory to ever have communicated, appear so similar? This puzzle, known as the horizon problem, inspired scientists to propose that the universe underwent a brief moment of explosive expansion, called cosmic inflation, in its primordial moments, smoothing out irregularities and linking distant parts of the cosmos before settling into a more measured pace of growth. Though indirect, the CMB's uniformity is a pregnant hint at this earliest phase, one far more dramatic and bizarre than anything seen since. And so, the hunt continues. Cosmologists now pore over the CMB, searching for even fainter imprints, signs of primordial gravitational waves from inflation, or subtle distortions that might reveal the properties of dark matter or neutrino masses, or even hints of new physics beyond our current theories. On a dark, cool night, when the stars come out and the world is quiet, there's something poetic in realizing that, bathing every corner of space, including this very planet and every living thing on it, is this ancient radiation. Every second, Hundreds of millions of these photons pass through your body. Fossil light, as old as time itself, the gentle, omnipresent afterglow of the Big Bang. The cosmic microwave background stands as a monument to the universe's earliest memory. It is the echo of Genesis, the signature of creation, a reminder that, though we are late arrivals in an ancient cosmos, we possess the tools and the wonder to listen to the past and peer into the beginning of everything. The CMB's quiet whisper, picked up faintly by our detectors, tells an unbroken story stretching from the fierce brightness of the cosmic dawn to the boundless, expanding present. It reminds us that, to understand where we are, we must search for the aftershocks of where we came from. The footprint of the Big Bang spans the cosmos itself, a legacy written in the oldest light, a testament to both the power of nature and the ceaseless curiosity of humankind.